Okay, so we're ready for the third lecture on elliptic curves. Just as a recap, keep the eye on the prize. We're going to talk about the Mordelve group of an elliptic curve, and the goal is for you to go home and say, I am in the 5%, I can solve this Diophantine equation. So we're learning elliptic curves through this meme. And we're trying to figure out how somebody came up with this huge solution to the problem. And this is the Diophantine equation in question, this projective version of the Diophantine equation. And what we did is we learned about switching models from a general cubic model to a Weierstrass model. And it is a long Weierstrass model. And then we were, okay, so what are the rational points? We found some. It's easy to find in this one. It's easy to find, for example, that 8 minus 8 is a solution. But that gives me something like minus 11 apples. And I can't have that. And so it does work arithmetically as an arithmetic solution. It's a very interesting solution, but it's not what we're looking for. And there are other points. We found that there is a torsion point. There's a point of order 6, this point, and that didn't work. And 2q, that didn't work either. It gave me 0 bananas. That's not good either. So let's learn more about points. Before I go more into points over number fields, over q, let's backtrack. What do we know about points over finite fields? For an elliptic curve over a finite field, there is only, well, the point at infinity, right? If I'm in Weierstrass form, there's a point at infinity. And then there is p choices for qx, p choices for q, or so for y. So it's like at most p squared plus 1 points. So there's only finitely many points every time. However, there is a heuristic, and I'm not going to do that here, but you can sort of like maybe try to come up with that heuristic yourself of why do we expect that if we have a finite field with, say, p elements or with q elements, q being a power of p, the heuristic tells you that there should be about q plus 1 points. And what Hasse did is actually prove that heuristic in that the number of points on an elliptic curve over a finite field with q elements is about q plus 1 with an error. And the error is 2 times the square root of q. Okay, so that is an interesting result. And as an exercise, well, let me show you one such example. Here's an elliptic curve over a finite field with 5 elements. These are all the points on that elliptic curve over that finite field. It satisfies Hasse's bound. 6 points is between 6 plus the error, which is 10 about, and 6 minus the error, which is about 1.52. It satisfies the bound. It's like sort of smack in the middle of the bound. But that bound of Hasse is not like, well, it's a bound. It is actually the best bound possible, because I challenge you as an exercise, find elliptic curves and a finite field such that the one elliptic curve such that it has the maximum allowable number of points over that finite field, and also an elliptic curve that has the least amount of points. Okay, and if you want a real challenge, find an elliptic curve that at one prime is minimal and another prime is maximal. Okay, so that can also happen. Not for the same prime, but for different primes, you can have like very little points, and for another prime, a lot of points. Yes? There are, definitely for the third option, there is some much better option than guessing and checking, yes. Yes, for the first and the second one, there are papers on this, elliptic curves with this many points or very few points. There's theory behind this. But to find one or the other, I think you can just do a quick search in, say, Magma to find these examples. But once you have one example of each kind, tried to come up with a way of coming up with an example that has this behavior for different primes without doing some like large computation. Okay, so this is what happens over a finite field. So what about Q? We're interested in the rational numbers or a number field like Q adjoint I, or Q adjoint the square root of 2, or Q adjoint some root of unity. What happens over there? Mordell proved what's the Mordell theorem for elliptic curves over Q. He proved that, yes, that the Q rational points, the Q points on an elliptic curve over Q is a group that is finitely generated. And they proved that for any number field and for any abelian variety, that is also true. Then Neron proved that this is actually true for any elliptic curve over a field that is finitely generated over its base field. So it is also true for elliptic curves over function fields with coefficients in finite fields. That's a mouthful, but it is also true there, and that's also important, as I mentioned in the first lecture maybe, about like Shafarevich's theorem or Ulmer's theorem about elliptic curves that have arbitrarily high rank in function field cases. So that's something we're really interested in. So those cases matter. So here's an example of a Mordell-Weil group. The elliptic curve y squared equals x cubed plus 1 has exactly 6 points. So it is a finite group of points. It is generated by 2, 3, and we had the addition law last time. Remember, if I do 2p, it goes here. We did that last time. If this is p, this is 2p, and so on. So this group is, it is finitely generated because it is finite, and it is in fact cyclic of order 6. Every point on this elliptic curve is torsion, and the rank is 0. There is no point of infinite order. This elliptic curve, as I said before, this is a famous elliptic curve. If you go to the LMFDB, this is called the Gauss elliptic curve because it was used to settle the class number 1 problem by somebody else. But in any case, this elliptic curve of rank 3, so this elliptic curve has no torsion, and the Mordell-Weil group, this is what we call the group of rational points. We usually say the Mordell-Weil group, and sometimes I will write MW group for it. That group is generated by 3 points. We'll come back to this example later on. And the torsion is trivial, and the rank is 3. What about the fruits Diophantine equation? If you look at this elliptic curve, well, this is an elliptic curve, but if you look at this Weierstrass model, I can compute the actual Mordell-Weil group, and it is isomorphic to this group. It's generated by a point of order 6 and a point of infinite order. So now that I have the Mordell-Weil theorem, I know exactly how every point comes about. It's a multiple of this point of torsion plus a multiple of this point of infinite order. So now I actually have a way to list all the points, and I can start, just see if I can find one that will give me a solution to the fruits problem that works. So every point on the fruits Diophantine equation will be exactly of this form. Okay, it will be a multiple of the point of finite order, and this n is just between 0 and 5 included, and any multiple of q, any multiple of this one for any integer. I can have q, I can have minus q, 2q, minus 2q, and so on. And it has to be, if there is a solution, it has to be one of these. And it turns out that as I do that, if I sort of like cycle through solutions, it turns out that 9q is the one I want. If you start cycling through solutions, there's always one coordinate that gives me some negative number of fruits until I get to 9 times the point q. And that's the first time that it turns out that every coordinate x, y, and z from the original model of the fruits Diophantine equation, every one of those x, y, and z are positive, and this is the smallest solution. So this is x, this is y, and this is z. And that corresponds to 9 times q. Okay? Okay, so very good. Okay, so again, the Mordell-Weil theorem tells me that that for any elliptic curve over Q, oops, I don't want to write like that. I want to use the laser. That for any elliptic curve over Q, I have this decomposition. So now we want to know what actual combinations can occur for elliptic curves over Q. So we start by trying to analyze this part of the Mordell-Weil group. What are the possibilities for torsion? So here are 6 elliptic curves, and for these elliptic curves, I have the following. Let me tell you what the torsion subgroup is for each one of them. Here is trivial, there's just O. Here is Z modulo 2. Here is Z modulo 3. Here is Z modulo 4. Here is Z modulo 5. And here is Z modulo 6. So these are examples of elliptic curves that the torsion is for the 1, 2, 3, 4, 5, and 6. So once you start seeing this, you might wonder, like, okay, so what torsion groups are actually possible as I go over all the elliptic curves over Q? And that is what Maser concluded. Search for that question of an answer to that question that had been already conjectured, as I said before, by Levi and reconjectured by Ogg. It was known as the Ogg conjecture when Barry Maser proved it. And now we know that there is, there's 10, 11, and 4 more. There are 15 possible torsion subgroups and no others over Q. If you go to other number fields, there are other possibilities. If you go to function fields, there's other possibilities. But over Q, these are it. And in fact, we have this theorem it also says that there are infinitely many for each kind, and we have cataloged what they are. So here's examples of elliptic curves with each one of the possible torsion subgroups and a generator. So this means that, for example, here, this elliptic curve, the group of order 12 is generated by the point 0, 2, 10. For this one that is not cyclic, but there are 2 generators, the point 2, 0 and the point 0, 0 generate the torsion subgroup that is isomorphic to Z mod 2 cross Z mod 2. And moreover, these, as I said, these families or elliptic curves with a certain torsion subgroup are organized, neatly organized in families, in parametric families. So for example, if you want to see what elliptic curves have a torsion subgroup or a subgroup isomorphic to Z modulo 5, it turns out they are in this family. So this family has the property that the torsion subgroup has a point over order 5. And if you have any elliptic curve A that the torsion subgroup has a point of order 5, then it is one of these. There is some value of t such that your curve is isomorphic to one of those. And this is sort of like a toy example of what we call a modular curve. So it turns out that elliptic curves with a certain torsion structure, if you set up some sort of torsion structure, if you say something about elliptic curves such that the torsion subgroup is of this kind, and by this kind I can say with this many points, or I can say with this Galois group, or this Galois group for the field of definition of these torsion points. So there's many ways in that you can sort of like talk about elliptic curves with some torsion structure. And if you do that, then we can actually construct what we call a moduli space, so spaces that parameterize elliptic curves with that property. And these moduli spaces turn out to be curves that are called modular curves that you might have heard of. And this is one example of a modular curve. This is the modular curve x1 of 5 that parameterizes elliptic curves with 1.05 torsion. Okay, so this is why there is such a nice sort of like construction, because it is actually the reflection of the fact that there is some sort of like general procedure of coming up with parameterizations of elliptic curves with a certain structure. And the reason why in Mazur's theorem, why 11 is missing, where did M11 go, is because you can construct a modular curve for x1 of 11 that would parameterize elliptic curves with points, with 1 point of order 11, and that elliptic curve has no points defined over Q. So there is no such elliptic curves. Okay, there's a paper that I really like. It's a classic of Tom Weston has a paper that is called the modular curves x naught of 11 and x1 of 11. That is an introduction to the concept of modular curve and explains why x1 of 11 has no points, constructs x1 of 11, and shows that x1 of 11 has no points. And it is a very, very nice paper if you want to learn that kind of thing. Okay, so yeah, modular curves. How do we compute the torsion subgroup? I would like, yes, question?
Do we know what kind of subgroups for torsion points we have for like general fields, not just Q?
So that's sort of like a big problem. We know for quadratic fields, if you have an elliptic curve or a quadratic field, then we know by work of Kenku, Momose, and Kameyani, we have a list of what possible torsion subgroups can appear. For example, you can have new things. You can have a torsion subgroup that is Z mod 4 cross Z mod 4 over Q adjoint I. That cannot happen over Q. But for larger number fields, we know what the classification is, what possibilities are there over cubic fields, over all cubic fields. We know what can happen over some specific cubic fields. We can tell you what options might be, but the question is open for degree 4 fields. I have some ideas. We know, for example, what are the ones that appear infinitely many times. But we don't know what we call sporadic groups, what type of torsion subgroups appear only finitely many times. Those are the hard part here. But then after that, there are some results for certain types. You know, if you are over a cyclotomic field, what torsion can happen, or if you're in a p-adic extension of Q, what torsion can happen, or in a billion extensions of Q. One of my graduate students solved that problem over Q. So if you start an elliptic over Q and base extend to an abelian extension, what kind of torsion subgroups can you expect? So there's a lot of questions that are of that type that are some specific cases are known. Okay, but in general, so if you have an elliptic curve over Q or over a number field, how do you compute the torsion subgroup? I'm going to teach you two different methods. One method is what's called the Nagel Lutz. These are two people that prove this independently. The Nagel Lutz theorem tells you that there's a very easy, simple algorithm to compute the torsion. So if you have an elliptic curve given by a short Weierstrass equation, then every point of torsion that is not just O satisfies the following. First of all, the coordinates of torsion points are integer points. So remember that Keith was talking about y squared equals x cubed minus 11, plus 11, and there were no integral points there. That is an equation that is in short Weierstrass form. So if there are no points with integral coordinates, then the torsion has to be trivial. But there was a point that had q rational coordinates. Immediately, I know that that point has to have infinite order. So immediately, once we have found one and we've proved that there are no torsion, now I know that that equation has actually infinitely many solutions over the rationals, which is a strong statement already. And actually, I can construct them by repeated addition of that point. We also have the second part is that, well, let me talk about this one. If P is of order 2, then the y coordinate is 0, and the x coordinate is a root of the polynomial in x. And if the order is 3 or larger, then the square of the y coordinate is a divisor of 4a cubed plus 27b squared. Remember that that quantity appeared in the discriminant, so it has to be with the discriminant of the elliptic curve. But this gives you a way to compute all the torsion. I know how to compute 2 torsion, and for any other order torsion, this gives me a list because I can compute this number and find the factorization and then find what squares divide that number. Yeah? Let me not go into the ring of integers. I think in the ring of integers, you have to be a little bit more careful. There are other tools like this that you can use in ring of integers to sort of like bound. So for example, this I'm sorry, what was your question again?
My question was, if you take this like same kind of equation, and your elliptic curve is now over a number field, and you have a torsion point over that number field, do the coordinates lie in the ring of integers analogously to how these lie in the integers?
I think that's no longer true, but so there are, depending on the number field, depending on the ramification in that number field, I believe you have a cap on how what can be the sort of the denominator of your integers. So you can sort of bound, it has to be in some sort of S integer ring that you can control. But let me not try to state this now in the number field case. But you can definitely, you get some similar statements to this over a number field. Okay, so let's see how this works in practice. In practice, if I have this elliptic curve here, this elliptic curve, well, over q, x cubed minus 2 has no roots. The cubic root of 2, there's no cubic root of 2 in the rational, so there is no 2 torsion at all. And then for a cubed minus 27 plus 27b squared, right? Yeah, plus 27b squared, that is 27 times 4. And then 27 times 4, if you look at what squares divide 27 times 4, well, then the y coordinate can be plus minus 1, plus minus 2, plus minus 3, or plus minus 6. And then if you take one of those, then I know what the x, so if this is that is square, then that it would tell me, so if, for example, if y is 1 or plus or minus 1, then x cubed would be 1 plus 2. So x cubed would be 3, which of course is not a cube in q, so that doesn't work, so this doesn't work. So x cubed would be 3, 6, 11, or 38, so none of them work, so there's no torsion over q at all. Okay? But again, this elliptic curve has a rational point, in fact has a point with integral coordinates. The theorem Nagel-Lutz tells you that if it is torsion in short value stress form, the coordinates of the torsion are integral, but it doesn't say that's not an if and only if. So you can have integral points that are not torsion. In this case, there is a point. Do you know a point on this elliptic curve? Somebody said it, but very quietly. 3, 5. 27 minus 2 is 25. So there is a point, 3, 5. So that point is not torsion. So it has to be of infinite order. So automatically, by proving that the torsion is trivial, I've proved that there are infinitely many rational solutions to this equation, which is a very strong statement. So there are infinitely many cubes that are 2 more than a square in the rationals. Okay, so that's an interesting fact. What is it? I mean, there could be more integral points. That's right too. That's right too. So if 3, 5 was a torsion point, for example, I can prove that 3, 5 is of infinite order by taking 3, 5, adding it to itself, see what the coordinates are. Those coordinates in this case are not integral, but if the coordinates of 2x of 2p are not integral, then 2p is not a torsion point. But if 2p is not a torsion point, p is not a torsion point either. Great. So that's an example. Now, going back to the fruits problem, I have my fruits equation. I can put it, by the way, in a short Weierstrass model. Remember that in magma it's Weierstrass model of E. I can put it in Weierstrass model and now use Nagel-Lutz. And what is that? If I want to see what kind of torsion there might be, 4aq plus 27b squared is this huge number. And you can see there are a lot of squares in there. So using Nagel-Lutz is going to be a pain in the butt because there's going to be a lot to check if you're doing it by hand. If you put it in a computer, this is going to be like a split second to do. But if I was going to do it by hand, I'm going to have to compute a lot of different possibilities for the y coordinate and a lot of possibilities for the x coordinate. So I'm going to teach you a quicker way of doing this using, again, finite fields. So we are interested in finite fields, for example, because of applications. You saw the factoring method by Lenstra, but we can also use finite fields to aid our research on elliptic curves over number fields. So what we do is, if you start with an elliptic curve over Q with a model that has integral coefficients, I can reduce every coefficient, and now I get an elliptic curve over a finite field. And after I've reduced, elliptic curve in question marks, I get a curve over a finite field. So for example, this one, I can reduce modulo 5, but when I reduce modulo 5, I get something that is singular. So that is not going to, this is not great, but it actually gives me some information about what's happening at 5. And by doing these reductions, I'm going to be able to get information back about the Mordell-Weil group over Q in 2 ways. First way I'm going to show you is that it gives information about what the torsion is. And second way, in my 4th lecture, I'll show you that the whole Birch-Sturm-Dyer conjecture is doing this for all primes and then saying something about what the rank is. So the finite fields, these reductions tell you both about the torsion and the rank. So what happens when you reduce modulo p? Just by example, here's things that can happen. You can have an elliptic curve, reduce modulo 7, and you get a curve that is actually smooth, so it is an elliptic curve. Great. If I reduce modulo 5, though, I get this curve, which is singular. It has a cusp. If I take this curve and I reduce modulo 5, I get something, again, this is probably, the picture is not accurate. We had a fight last time about this. But let me just say that intuitively, that what happens is that there is a self-intersection. And what that means is that if the picture looks like this, then it's multiplicative reduction. And that, because in this case, the slopes are actually in F5. Those we call split multiplicative reduction. And if you do the same thing, but the slopes, oh, this is a 7. If you reduce modulo 7, though, the slopes are no longer in the base field, and they are in an extension, and then we say it's a non-split multiplicative reduction. Okay, though these terms will come up when I define the L function of the elliptic curve. So keep that in mind. But the key point now is two things. One is that I can detect all the primes of bad reduction, and there's only finitely many. It turns out that if you have a prime of bad reduction, then it divides the discriminant of your model. So because the discriminant is an integer, there's only finitely many primes of bad reduction. And in fact, if the discriminant is minimal, so minimal, I haven't talked about it, but you take a model, and then I can do all the possible isomorphisms of that model and then look at all the discriminants. The model that has the smallest discriminant of all that are isomorphic, that is the minimal discriminant because it will have the least amount of primes that could divide it. And that one tells you actually the if and only if that P is of bad reduction, if and only if P divides that minimal discriminant. So I can detect what are the bad primes. And then if I know that, take an elliptic curve, P a prime number, and M bigger than 1 that is relatively prime to P, and suppose E has good reduction when I reduce it modulo P, then the M torsion of my elliptic curve over Q actually embeds, because this is an injective homomorphism, it embeds into the point over FP. This I can easily compute, and that gives me information about how big this can be. This group can be at most of order m squared, and in fact the order divides m squared. So by knowing that the order of this could divide m squared, and the order of this, for example, if this is a 7 and this is a group of order 10, well then neither 7 or 49 divides 10, and then I can rule out 7 torsion. I'll show you in a moment how that works. But in particular, the number of points in here has to divide the number of points over Fp. So for the elliptic curve with the fruits elliptic curve, the discriminant is this, 2 squared times 5 times 7 squared times 13 squared. So 3 doesn't divide the discriminant, so 3 is a good prime. So I can use that theorem, and by counting, I see that there are 6 elements over F3. And what this tells me, and I'm going to leave this as an exercise for you, there are examples in the book about how to do this, but what this tells me is that any torsion that is not 3 torsion, it has to divide the order of, if you have 7 torsion, 11 torsion, and so on, that order would have to divide 6. So this alone tells me that there can only be maybe 2 torsion or 3 torsion. Okay? And when I look at the prime 11, this tells me that for everything else, the torsion order would have to divide 12. So again, it tells me that there's only 2 torsion and 3 torsion. And then I can just look at the 2 torsion and 3 torsion and determine what 2 torsion and 3 torsion do I have. And by the way, there's only at most order 6. And it turns out, so that tells me that the torsion subgroup is at most of order 6. But we did know a point of order 6. So the torsion has order 6 without having to do all these square divisors of 4a cubed plus 27b squared. Yeah.
Sorry, can you go back a slide? So the reduction mod P is an injective homomorphism from the points on the elliptic curve.
Of m torsion. So those are points of order dividing m. So m is an arbitrary number. If m is any number that is relatively prime to p, then the m torsion embeds into the number of points modulo p. So the way you use this is that, okay, I want to know, is there 7 torsion? All right? So I take a prime, like say 3, that is good, and I want to know, is there 7 torsion on my curve? 7 doesn't divide, 7 is not divisible by 3, 3 is of good reduction. I compute this, and what I did in the next page is that this is 6. So this tells me that the 7 torsion defined over Q, if there was any 7 torsion, it would have to embed into a group of order 6. But the 7 torsion, it turns out, well, it has to have order, a power of 7. So it has to be a power of 7 that divides 6. So it has to be 1. So the 7 torsion, the order of the 7 torsion is 1. And this applies for any prime that is not 2 or 3, that order has to be 1. So there cannot be any torsion that is not 2 or 3. Once I know that for p equals 3, this is of order 6. Okay? Yeah.
So are we implicitly here saying that all elliptic curves have like a minimal integral model that we can use? Is that a fact?
Yes. Oh, over Q.
Over Q.
Over Q, there is always some model, and that's it's easy to prove because you take one elliptic curve, you can find an integral model by doing a change of variables that kills all the denominators of the coefficients. Once you have one integral model, now I can look at all the other integral models that the elliptic curve is isomorphic to, and then do the subset of the absolute values of all the discriminants. Then there's got to be a minimal element, and that discriminant is that is your minimal discriminant. Yeah. Okay. So now, before I move on to other things, I want to, because this is going to come up in Christel's course, and in fact, I think Keith already also mentioned today in his course, elliptic curves with complex multiplication. So I want to tell you what an elliptic curve with complex multiplication is. A lot of my research actually recently has also had to do with elliptic curves with complex multiplication. So what is an elliptic curve with complex multiplication? Take any elliptic curve over a number field or over any field, and n bigger or equal to 1. We have a map that sends E to E by sending P to n times P. Just add P n times. N could be negative. I can compute minus P and then multiply that point to itself also. Okay. So this is an endomorphism. This is actually an algebraic map. The addition on an elliptic curve is an algebraic map. And this is an endomorphism of your elliptic curve such that it has this property that when you compose multiplication by m with multiplication by n, you get multiplication by nm. The endomorphism ring is a ring because it has two operations, addition and multiplication being the composition of endomorphisms. And what this says is that I can actually embed the integers in the endomorphisms by, what I actually mean is that the integer n is the multiplication by n map is in there, and then that's a subring in the endomorphism ring. Okay, and the question is that all? Are there more endomorphisms on an elliptic curve? And it turns out that there are some that do have more endomorphisms. So, for example, this elliptic curve. This is an elliptic curve. We have me and my students and many people have a love-hate relationship with this elliptic curve. This is an elliptic curve with j equals 1728. Love-hate, because they're very difficult to deal with. There are, in some cases, they're very easy to deal with, and then in many other cases, they're just like, what?
Not this one.
Well, this one as a representative of the entire family of elliptic curves with j equals 1728. So their arithmetic, it turns out to be quite complicated once you get into the weeds of it. But it's really interesting that it has an extra endomorphism, which is multiplication by I. So multiplication by I, if I take a point on this elliptic curve, I can send it to minus x naught, comma I y naught. You can see that this point, if this belongs, this point also belongs because of the I will give you a minus here, and this gives you a minus in the whole thing. So it belongs. So it's an endomorphism of the elliptic curve. And in fact, now I can compose it with multiplication by n maps. I can add it or multiply by multiplication by n, and I get a whole lot of endomorphisms. And this subgroup of endomorphisms is isomorphic to z adjoint I. okay, which is a ring of integers. And it turns out that the endomorphism ring is isomorphic to Z adjoint I. Why do we call it complex multiplication? Sure, there is an I here, but this definitely does not look like complex multiplication. There's just some gadget that works. But there's a reason, which is, remember we talked about elliptic curves over the complex numbers, that an elliptic curve over the complex numbers is isomorphic to a quotient of the complex by a lattice. It turns out that the lattice for this elliptic curve is Z adjoint I, or you can take the lattice to be Z adjoint I, and that quotient gives you an elliptic curve that is isomorphic over the complex numbers to this one, okay? And in this lattice, I can do also I can do endomorphisms of this lattice. We do have multiplication by ends, and Z or Z modulo this ring, Z to NZ, that is an endomorphism of the lattice, of the quotient. And there is one more, which is really complex multiplication. This is like complex numbers multiplying together. So it is literally complex multiplication, and it sends Z to I times Z. In general, if this is an arbitrary lattice, that doesn't have to work, because you have to make sure that this is well defined, that the class of Z modulo this lattice being sent to here, that it doesn't depend on the representative I choose, but because of its Z adjoint I and I'm multiplying by I, it turns out you can prove that this is well defined. And we can put it here. That is what this word is about. Exercise, you do it. So prove that this is well defined. Okay, so that is an endomorphism, and now it's clear that any such thing is an endomorphism, and you can see it's really multiplying by a complex number. That's complex multiplication. There are more elliptic curves even over Q. This elliptic curve also has a complex multiplication, which is that take rho to be a non-trivial root of unity, a non-trivial third root of unity. Then I can send this point to this point. The cube here will kill that row, and then I get an endomorphism. And it turns out that in this case, I have that the endomorphism ring is Z adjoint rho. Okay, is the what are these called? The what integer? The Eisenstein integers. So here are some facts about complex multiplication. First of all is that if you have a number field over other types of rings, there is all sorts of some other crazy endomorphism rings, but over a number field, so over Q, the endomorphism ring is always the integers, and that is the generic case. Okay, don't go thinking that there's lots of complex multiplication. Complex multiplication is rare, so most elliptic curved endomorphism ring is just a multiplication by n maps, or a order, an order in a imaginary quadratic field. So it can't be just any order. It has to be essentially like a maximal, like a ring of integers of an imaginary quadratic field, or some sub-ring in there. And moreover, really interesting is, and this is the connection, one of the first connections with class field theory is going to be here, is that if you have an elliptic curve over Q and the endomorphism is an actual ring in an imaginary quadratic field, then the class number of that order has to be 1. And that alone tells you there's only so many imaginary quadratic fields of class number 1, and there's only so many subrings of orders of imaginary quadratic field that have class number 1. But in fact, there is only 13. So remember that there is a J invariant. There is an elliptic curve with any J invariant. So there is infinitely many elliptic curves over Q that are non-isomorphic, but only 13 of them, for 13 J invariants, actually have complex multiplication. 2 examples being J equals 0 and 1728. But there is more. Okay, so I think I'm going to go back to rank tomorrow. So I'll stop here for today.